Okay, so this lecture is basically about the kind of underlying probability in machine learning that you're going to need to understand to kind of understand the rest of the class, right? So when I kind of specified the requirements for this class, I said basically some undergraduate course in machine learning, and kind of what that implies is that you also understand something about calculus and probability and linear algebra. And so I'm going to talk about some of the key things that I expect you to understand both today and then on Thursday, okay? So by the end of this week, you should have a very clear sense of kind of like, am I prepared mathematically for this class, right? Okay, so let's get into it. So today is going to be a pretty, kind of paper and pencil, notes-heavy lecture. So probability in machine learning. Both of which are obviously courses that you could, spend a whole semester on each of these things. So I'm going to give you just like the total Cliff Notes version of what I think is kind of most important right now, okay? So key concept from probability that hopefully you'll remember is a PDF, right? Probability density function. So probability density function. Which we abbreviate as a PDF. Okay, P of x, usually we call it. Okay, and so this is defined over some sort of a continuous space, right? So when we're teaching like first undergraduate probability, we may have a picture that looks like this, and we know that the picture here kind of tells us, if I give you an interval over the real line, I can compute the probability of that interval by doing an integral, right? And so before I forget, so this is kind of like the continuous version of a PDF. Now, most of the time in anything computerized, we are dealing with actually discrete things under the hood, right? So oftentimes we may discretize something. So if I have a discrete domain, then this is more like kind of a bar chart in some sense, right? We call this technically a probability of mass function. But with some, it's not really even abusive notation, because one thing that I always do when I teach undergraduate probability is to say that actually if you think about these bars as delta functions, right, that a PMF is really exactly the same as a PDF. It's just a special case of a PDF where you can only achieve a certain number of outcomes, okay? So without kind of loss of generality, I'll always just talk about PDFs, even though sometimes under the hood we may be talking about something that looks more like this, okay? And before I go on, let me just remind you that if any of this probability stuff seems like a little bit fuzzy in your mind, I have a whole set of lectures on probability. If you go to the resources section of the website, you can get to these probability of bytes videos, right? So I made these, I made these for remote lecturing, but I think that I'm still using them today whenever I teach probability. So these are basically like 10-minute bite-sized lectures on everything that you need to know, right? So for example, if you're looking to brush up on PDFs, you could watch this lecture 28 on PDFs, right? So anything I'm saying here, if you need to go back for a little bit more, tutorial stuff, this is where you can find it, okay? It's on my YouTube channel. I think it's also on MediaSite somewhere. Okay, so basically this domain here, we call it the sample space, and we are looking at a way of estimating, what's the probability of getting an outcome in a certain region of the sample space, right? And so one kind of important thing is that these PDFs and also these PMFs have to sum to 1, right? There's kind of one unit of probability that can be accounted for across the whole axis. We can't have anything like a negative probability. That's not legal. And so, but any other function that kind of satisfies those requirements will make it work, right? Now, a common mistake is that the PDF is not the probability of getting an outcome, right? So, the PDF P of x is not kind of colloquially the probability of getting x. Right, the reason for that is that if I think about a PDF that there are an infinite number of possible outcomes on the x-axis, right? And so if each of these guys had some sort of non-zero probability, I would certainly add up to 1 like super fast, right? So it's not possible to assign each of these individual places a actual probability of getting this value, right? In fact, the probability of getting any particular value is 0, right? It has to be 0, otherwise nothing could add up, right? So for example, if I'm saying pick a number at random between 0 and 1, the probability of getting exactly 0.5 is 0, right? That's something we talk about kind of in a couple weeks into probability. The thing that the PDF does tell us is what's the probability of getting an answer that's in a certain region, right? So for example, if I wanted to know what's the probability of being inside this little interval here, say between 5 and 6, what I would do is I would integrate the PDF from 5 to 6, and this would give me the probability that the random variable is inside this range, right? And I can kind of think about, again, as a limiting argument, if I wanted to say, okay, what's the probability of getting 5.5? If I kept on shrinking this interval, you could see there'd be less and less probability until eventually I get 0 probability. That's why the probability of getting any single value is 0, right? We can only talk about the probability of getting something in a range, right? So in general, the probability that x is in some region is the integral over that region of the PDF dx. And this could happen in any number of dimensions that you want, right? Now, the only case where this is kind of true is here. But again, if I think about these as delta functions, then everything is still OK, right? That's like saying that if I have, flipping a coin, either I could get 0 or I could get 1. And each of these delta functions has height 1/2. When I integrate over this delta function, no matter how small of an area I get, I always get the value, the height of that delta function, right? So that's kind of like why each of these things gives me a non-zero chunk of probability, and there are only 2 places on the whole real axis where that can possibly happen, right? Okay, so this is the idea of a PDF, right? And you should remember that there are kind of like these important things that then we can extract from the PDF, right? So expected value and variance and stuff like that. So let's talk about that for a second. So we will often talk about the mean or the variance of a distribution. So the mean or the expected value, we will say, sometimes we'll call it mu sub x, sometimes we'll call it expected value of x, is just taking the PDF and performing this integral, right? And so the idea is that, the mean of x is something that we expect to be, it's not the most likely value, but it's kind of like that. It's the middle of the distribution in some sense, right? The variance is defined as the expected value minus the mean squared. So this is the mean, this is the variance, which is like saying I take my x minus mu x squared p of x dx. And sometimes we also talk about the standard deviation, which is the square root of the variance. Okay. And this all generalizes to multiple dimensions as well, right? So I'm kind of defining things in 1D, even though we know that actually in our class we're going to be dealing with things that are like extremely super high dimensional, okay? But all of it kind of carries forward. Okay. So like we talked about before, this generative modeling stuff that we're going to spend most of our class time talking about, basically has to do with estimating a good PDF based on looking at examples from data, okay? So let's just say that on a piece of paper. So, generative modeling, so maybe I should start back at machine learning, right? So machine learning, kind of in general, and generative modeling in particular, have to do with trying to get good estimates of PDFs. So we're trying to estimate a PDF, let's call it P model of X, that gets close, that approaches some true data distribution. We don't know the data distribution. We just see examples of it that come from a bunch of things that we were given, right? And so if you've ever taken a machine learning class, you may have seen different ways of doing this kind of probability density function estimation problem, right? So maybe you heard of like, Parson windows or k nearest neighbor, stuff like that, where we see a bunch of data points and we build up our model of what a PDF should look like from those data points, right? That's kind of one way of talking about like a kind of a nonparametric density estimation, it's called. However, to make this whole problem tractable, oftentimes what we need to do is make our model of the PDF simpler, right? We have to describe the PDF by some simpler set of numbers, right? So to make this more tractable, what we often do is parameterize the PDF. With some finite number of parameters. Let's call that theta. And so that if I tell you theta, that basically generates the model, okay? So I can think about these theta values as just kind of like knobs that I'm allowed to turn to generate different kinds of PDFs, okay? So for example, one of the most common PDFs in machine learning and elsewhere is the Gaussian PDF, right? So for the Gaussian, what I would say is, in 1D, the Gaussian PDF is the following. So it's 1 over square root 2 pi sigma e to the minus 1/2 x minus mu squared over sigma squared, right? This is kind of like the famous bell curve where kind of it's centered around mu, and then sigma kind of tells me whether this is a tall, skinny function or a big, broad function, okay? And so here, basically, the mu and the sigma, if I tell you those two numbers, that fully specifies the entire Gaussian PDF, right? So I've got a much more, I've got a complicated function that is boiled down to just these two numbers, okay? And one of the, things that we learn in probability is how kind of endemic the Gaussian PDF is across all sorts of natural phenomena, right? So one of the big things that we learn about is kind of like the central limit theorem, which says that if I add up a whole bunch of random variables, no matter how weird they are, if they're all identically distributed and independent, eventually I get something that approaches this Gaussian bell curve, right? That's why I could take, the heights of kids in kindergarten and add them up, and eventually I'd get a bell curve kind of thing, right? No matter how those heights are actually distributed. So so hopefully you've come across the Gaussian PDF before. And in higher dimensions, we would generalize this, right? So in higher dimensions, we would have this kind of PDF. So if I have, n dimensions, then I'd have square root of 2 pi to the n, this sigma in the denominator, e to the minus 1/2 x minus u transpose sigma inverse x minus u, right? So here, now, this is basically an n by 1, vector of means. This is an n by n matrix of what are called covariances. And then again, just some linear algebra notation that hopefully you're familiar with, right? So this thing here is the inverse. This thing here is the transpose of a vector. This thing here is the determinant of a matrix. right? So all that stuff is kind of like basic kind of calculus terminology that I'm spitting out along the way, right? So the key idea here is that now the parameters are basically, I've got a real valued vector of n mean numbers, and I've got a symmetric n by n matrix, positive definite matrix of covariances, okay? So most of the time, of course, in probability, we talk about all sorts of other distributions, like exponential and uniform and Rayleigh and stuff like that. That's not so much of a big deal in our class, right? Most of the time, things are going to be Gaussian, right? So as long as you're down with the Gaussian distribution, everything should be OK. OK, so let me pause and ask any questions or comments so far. OK. So now, in a huge neural network, I can think about the parameters of the neural network being all of these weights and kind of choices that I make inside the network, right? So there are billions of potential parameters, and in fact, it may be very hard to describe the network kind of explicitly. I mean, of course, there's like you download this from GitHub and you've got these billions of parameters, but to kind of write down all the list of parameters is probably pretty hard to do. So it's easy to do for Gaussians and hard to do for like these huge neural networks, okay? But in general, the name of the game is that I want to make my data model and I want to make my data distribution and my model distribution come as close together as possible, right? And so that when I parameterize the distribution by something like these variables theta is something that you would call an estimation problem, right? Find me the best parameters that drive these two PDFs to be as close as possible together, right? So the goal of a lot of machine learning is, the goal is to find the parameters theta to kind of best match the training data. Right? Now, best here has a bunch of possible connotations, right? So again, if you took machine learning, you probably have some idea of like, you may have heard of Bayesian estimation or maximum likelihood estimation. So again, in our context, almost all the time we're talking about what's called maximum likelihood estimation, okay? So, in our class, we're generally doing what's called maximum likelihood estimation. As a sidebar, there are other ways of doing estimation, right? So Bayesian estimation is a really important thing where if I already have some sort of a prior model for what these parameters theta should be, then I want to kind of nudge my model to kind of obey my prior estimates of what I think the parameters might be and balance that with what the data is actually telling me. But in practice, in our kinds of problems, we don't really have these kinds of priors to worry that much about. So we're going to stick with maximum likelihood estimation, which is sometimes viewed as being kind of like an agnostic prior, okay? So to do this, we have to kind of define what does this mean, likelihood, right? So what does that mean? All right. So if we have an observation X and a model that's parameterized by theta, then the likelihood is just, the PDF defined by the parameters theta evaluated at X, right? This is just the value of the PDF at X. Right? So if I have, here's my PDF, I tell you X, this here is just going to be the likelihood at X. Now again, remember, it's important to remember that this is not the probability of X, right? It is true, so it's good intuition, right? So when the likelihood is bigger, that means that if I take a small integral of a region around X, That number would be bigger if x is more likely and smaller if x was like over here somewhere. But again, the value of this number could be 0.05 or it could be 25, right? Depending on how tightly peaked the PDF is, right? So definitely don't mistake the likelihood for actually being a true probability. And of course, unfortunately, when you're looking at papers and reading books, sometimes there's a little bit of an abuse of notation, whether you're talking about like a big P or a small p. You just have to kind of be careful thinking about, am I talking about an actual probability or am I talking about a likelihood, right? That's kind of something that's important to keep in mind. Okay. So, of course, in machine learning, I don't just have one example that I'm showing my model. I have like hundreds or thousands or millions of examples, right? And so kind of what I want to know is what is the kind of joint likelihood of seeing all that data for a given set of parameters theta, okay? So if we have many what are called IID observations, this stands for independently and identically distributed. Then the joint likelihood, right? So kind of what I want is, what is the likelihood of seeing all these k observations together? I kind of decompose that into just the probability of seeing each of these things independently. Right? This is like the product of each of these things individually. Now, these likelihoods could be very, very small numbers, right? So, every probability is less than 1, right? And if I imagine that I have like, 1 million observations in my data set, I'm multiplying a million numbers together that are all less than 1. This number could be like super duper small, right? So for kind of computational and practical reasons, we often look at what's called the log likelihood, right? So we usually consider the log likelihood, which is this log of the joint set of probabilities. And we know that the way logs work is that products become sums, right? So this would become the sum of a whole bunch of logs. Okay. Now again, since these are all small numbers that are less than 1, the log of some number between 0 and 1 is going to be negative, right? And so typically when we're talking about like calculus problems, often the way that we're going to pose almost all these problems is by minimizing some sort of a cost function, right? Where we want the cost function to be low if the model is good. And so in some sense, what we want to do is flip the likelihood around, right? So we're going to take this log likelihood and we're going to turn it into negative, right? So since we usually care about minimizing a cost function, that means that the theta that fits the best is the theta whose argument is basically the minimum of the negative log likelihood. Right? So find me the theta where this set of likelihoods is as small as possible. Okay? Okay. Now, before I go on, let's just say that, how would I find this actual minimization problem, right? We're going to talk about it a little more next time. In calculus, we learned that we take the derivative of a function we set equals 0 to find the minimizer, right? That's all great until you have like a billion parameters or more in your network, right? It's not so easy to actually even write down what the derivative of this function should be, right? So we're going to talk about kind of clever tricks to kind of approximate what this minimizer should be. We'll talk about gradient descent, backpropagation, and stuff like that. But this is kind of like, again, the theory that we're going for. OK, so let me stop and ask any questions or comments so far. I mean, I feel like this is almost everything I want to say from machine learning, which I talked about in like, less than half an hour, even though the course is like, a whole semester long, right? But I think this is the most of what I want to talk about from probability, right? So, key concepts: PDF, Gaussian, maximum likelihood estimation, right? And so again, if you're looking for, refreshers on those, you might want to go back and just watch the videos, especially, in my class, when I teach probability, we usually get to the estimation problems kind of towards the end of the semester. People are already kind of like checked out. So it's good to go back and look at those again with fresh eyes at the beginning of the semester in case that doesn't, ring a bell from when you were taking it with me or with somebody else, right? Okay. All right. So let's talk a little about kind of basic machine learning, right? What machine learning stuff do you kind of need to know? And this is going to kind of, smoosh a little bit into our next class as well. All right. So basic machine learning. All right, well, I'm sure that anyone who took a machine learning class learned about the most simple neural network, which is the perceptron, right? So I'm going to talk about the perceptron for a few minutes, right? So, when we talk about deep neural networks, convolutional neural networks, the key question is neuron, right? What does neuron mean? So the most basic unit of a neural network is the neuron. By which we usually mean a perceptron, it's called. So perceptron is a super simple machine, right? So the input is an n-dimensional vector. Let's call it x from x1 to xn. I generally try to draw my vectors as columns, although sometimes you may end up having to draw them as rows for ease of use. The output is a scalar y, okay? And then the perceptron is basically just something that will combine all these inputs together to give me a number, right? So perceptron is nothing more than a function basically saying, the easiest thing is to take the signed value of a bunch of weights on these x's plus some constant, right? So this is basically like saying, this is the signum function that's just, -1 if I'm below 0 and +1 if I'm above 0, right? These w's are called weights, and this b is called the bias, okay? And that's one of the first things that you would do in a class is say, okay, I've got a bunch of input variables that I want to see if I can kind of predict the output variable, right? So for example, I am trying to find a movie to watch on Netflix, and so the x's are a whole bunch of features of the movie, how long it is, what kind of genre it is, and so on, how I'm feeling, how hungry I am, and then I train my neural network with a bunch of examples of inputs and did I watch that movie or not, and now Netflix has a model for, will he watch the movie under these circumstances, right? And so one thing that I can do to make this a little bit more mathematically compact is basically to say, well, if I include, if we let, x0 equal 1, right? Meaning that in addition to my 1 through n values of x, I kind of define this dummy variable x0 that equals 1. Then I can make my perceptron output much easier by saying it's just the sign of w transpose x, or the dot product w dot x, right? This is called the dot product. Super simple thing, okay? And then this w0 is going to be equal to the bias. So a lot of times, you'll see machine learning books will often kind of start by separating out the weights and the biases as separate things, but eventually, just to make the notation a lot more easy and tractable, they will kind of collapse the weights and bias into one single vector that kind of says, this is what I have to learn at this neuron. Okay? And so the activity of setting these weights is equivalent to building a hyperplane that goes through n-dimensional space, right? So the result is basically a line that goes through nd space, and everything on this side of the line gets +1, and everything on this side of the line gets -1. And these are my data points, right? And again, you can imagine that the goal of training the network is to move these points around, move this line around, so that if I said, okay, these red dots were actually labeled +1s on my data set, and the black dots were labeled -1s, I want to move this line in such a way that I, for example, have the best classification of red dots on one side of the line and black dots on the other side of the line, right? Of course, there's only so much I can do with this one line, right? We know that what's called decision boundary in the real world is much more complicated than this single slice, right? And so that means that I need more neurons and probably more layers too, okay? So to make more complex decision boundaries, need more neurons and more layers. So a classical example from neural networks is that you can't build the XOR function out of one slice through the plane, but you can build it with two slices through the plane, basically. So, and also, again, I'm not going to get into it a whole lot because this is not fundamentally like a teaching you machine learning class, right? But there's a theorem that says more or less that you don't really need any more than 3 layers of a network to have the most complex decision boundary that you can imagine. But nonetheless, modern deep learning networks are like, possibly dozens of layers deep, right? And again, I'm going to try not to let my own machine learning bias kind of come through here, but so much of modern machine learning, at least to this old dog, is just like impenetrable tweaking of a zillion knobs, right? Like the picture I showed you on the first day of class of the mixer console with all the knobs, right? To me, that's my mental model for the way that deep learning works, right? So, people are proposing all sorts of different ways of arranging these layers together. And a lot of what has been found to work well, both in terms of the architecture of a network and how to optimize it, is all just, it seems to work, right? Like this seems to work the best of all the stuff that we've tried, right? There's not, to me, a lot of really satisfying theory behind why this and not that. Of course, I'm not a machine learning researcher, so I'm sure that for machine learning researchers, there is a lot of interesting theory like that. But to me, it's just a black box, right? So that's why I don't really care that much about what's going on inside the black box. That's just me, though. OK, so how do modern machine learning algorithms go from just this perceptron to more complicated things, right? So for one thing, it's not typical that you actually see this sine function in there, right? So more typically is, typically we use what are called activation functions. Like, for example, the sigmoid function, right? So the sigmoid function is something that has that kind of like step function character, but instead smoothly goes from 0 to 1, right? This is called the sigmoid. It has a nice equation. Another thing that you may see is basically the hyperbolic tangent function, right? So the hyperbolic tangent function kind of looks similar, except it goes from -1 to 1. This is, tan h of x is e to the x minus e to the minus x over e to the x plus e to the minus x. The advantage of either of these functions over the step function is that they're differentiable. And that will become important. Either we'll talk about this time or talk about it at the end of next time, right? So these are kind of like, smoother versions of this step function, okay? Other things that you may see are, I'm sure that anyone who's done any sort of machine learning has seen, the ReLU function. So you may see a function that looks like this. Basically, it's 0 here, and then it's like, if x is greater than 0, it's just x. It's 0 if x is less than or equal to 0, right? This is called the ReLU, or rectified linear unit. And then there are modifications of this ReLU. For example, one modification is the same on this side, but kind of a different slope function on this side. So this is called the leaky ReLU. And so we're going to use different activation functions at different points in the network for different performance reasons, right? So, you're going to find that when you read a paper about a machine learning architecture, that it will tell you, okay, we used ReLUs at this layer, we used tan H at this layer. So that's just kind of like, again, what turns out to have worked well. And whenever you're building a network, you can just very easily swap out what activation functions you want to try out at different points in the network. So, we use different activation functions. At different points in the network. Basically to get the best fit, to have the best performance. So there are lots of rules of thumb about where you use the ReLU, where you use this thing, and a lot of it is that's all it is. Rules of thumb for what works in certain situations, right? This is one of the things, like, again, kind of bothers me when I read the how to learn deep learning kinds of books. It's like, part of the fun of deep learning is to try different things out and see what works. To me, that's not a lot of fun personally. Like, I just want something that reliably works. But anyway, so you're going to be, if you're ever going to train your own network from total scratch, there's going to be a lot of screwing around with what should I use at different layers and what activation functions should I use and so on, right? That's just the nature of the beast. Okay. So any questions or comments so far? All right. So a couple other things I want to talk about today, just in terms of some terms that you're likely to come across, okay? So you will definitely see at some point in your machine learning reading something called softmax, right? So there's kind of like a multi-input, multi-output activation function called softmax. So all that is basically I have a vector coming in. I put it through a softmax. What comes out is a vector of the same length, where each of these y's is kind of like a scaled version of what goes in, right? So the idea is that I try to scale the outputs to sum to 1, right? So the outputs sum to 1, okay? And the reason I might want to do that is so that I could interpret these outputs, for example, like a PDF, right? To say, okay, or maybe a PMF is more accurate, right? A probability mass function to say, okay, now I'm going to take the output that has the highest, number after the process, right? Yes? No, xn through xn are scalars, right? So it's basically a vector comes in and a vector comes out. Right? So they're not samples, they're actually vectors, right?
Because the output should be just one class.
Well, that's what I'm saying is this is a multi-output, right? So basically it's like saying if I have, say I have these numbers are my input, I put it through softmax, what comes out is this pair of numbers. Right? Now these numbers sum to 1, right?
Which is not the convention I usually use. Oh, yeah.
Am I saying it wrong?
No, it's
You guys know better than I do about some stuff, right? But this is the way I understand softmax.
referring to just the softmax after plus the argmax. We got
Oh yeah, so if you did an argmax after the softmax, then you get the maximum of these numbers, right?
What I usually do is I just have vectors for x1 through xn, and each of the elements in the vector correspond to the actual classes instead. So instead of just parsing each vector once, I would just pass in the entire matrix, and it would give the results for each of the vectors. It doesn't
Well, yeah. So you could think about this as a matrix-wise operation where I could pass in a whole bunch of things and I could normalize each of the columns separately, right? That would be fine. Yeah. And let me just say that I'm sure there are people in this class who know a lot more about this stuff than I do. So please feel free to chime in if I'm butchering something or at least saying it wrong, because I am no expert in this area, despite my authoritative stance here. Okay. All right. So just to recap, generally the goal of a neural network kind of training problem is to bring the predicted outputs as close as possible to the real outputs that I have in my training data, right? So kind of the goal is, so the neural network training is the following, right? It's like saying I have, here, just to kind of be clear, I guess that I try to do some annotation. So here I'm using superscripts for data samples, each of which are vectors, right? Now these can all go through the model, parameterized by theta, which is what I'm trying to tune, right? And then the model is going to produce a bunch of predictions of what the outputs should be. These are all predictions. These are inputs. And then I have what I would call ground truth, right? And what I'm trying to do is I'm trying to move the parameters of the model around to bring these y hats as close as possible to the corresponding y's, right? That's the whole idea of neural network training, right? And so now we need to have a cost function or a number that tells me, okay, how well did I do in this matching, right? So now we need this concept of what's called a loss function, okay? So to measure how well we did, we need what's called a loss function. And in this case, it seems like it's pretty obvious that if the y hats and the y's are both kind of continuous numbers, then what I should be doing is I should just be kind of summing up the differences between y and y hat, right? And so if these guys are both continuous valued, then it makes sense to use what's called the mean square error, right? So if the y's and the yi's are both continuous, it makes sense to use what's called the mean squared error loss function. Right? That's basically saying what I want to do is average over all my samples the difference between what I know is true and what the model predicted. I guess actually I put these like this, right? And I want to square this because I want to make sure that positive and negative errors count the same, okay? And this is also known as regression, right? So if you've ever done kind of fitting points to a line or something like that, regression is also the natural word for this kind of continuous situation, right? Okay. Now, on the other hand, sometimes I'm not trying to predict a continuous number. Sometimes I'm trying to predict basically a binary number, like am I in class 0 or am I in class 1, right? In that case, it makes sense to use a different function called the binary cross entropy, right? So if the truth is binary, and these predictions are in the range 0 to 1, like a probability, then the natural loss function here is what's called binary cross entropy. Or BCE. And the way I'd write that would be to say over all my samples, yk, I'm sorry, I guess I'm putting the subscripts on the y's now because I'm just too used to it. This looks a little bit confusing because it involves both the truth and the predictions. But basically the idea is that we want the loss to be 0 if the labels agree exactly, right? And we want the loss to be huge if the labels disagree, right? So for example, if yk equals 0 and the prediction is equal to 0.01, well, then that's great because this 0 multiplies this and it's very small, right? If the yk equals 1 and this yk is like this, that means that this is going to be like 1 times this thing, which is going to be really large. As this is negative, this is going to be contributing a big chunk to the binary cross entropy, right? So this is going to be good. This is going to be bad. But this is kind of like what makes sense where, oftentimes what's happening is that what comes out of the network is this kind of like, fractional value between 0 and 1. And then I may do a threshold just to say, OK, if it's greater than 0.5, I assign it to class 1. If it's less than 0.5, I assign it to class 0, right? The phrase cross entropy, there are kind of like historical reasons why this word is used. For those of you that are graduate students and know more about like information theory, this comes from the Kullback-Leibler divergence between functions. For our purposes, we just need to know that both minimizing the mean square error and minimizing the binary cross entropy loss are both kind of like the right thing to do with respect to maximum likelihood estimation in both of those cases, right? So kind of let me just say that under the right circumstances, minimizing the mean squared error or the binary cross entropy loss is doing maximum likely estimation, which is really what we wanted to do in the first place. OK. One thing that doesn't come up that often, but I'll mention it in passing, is that there's also something called the categorical cross entropy. So that's in a situation, I can just write this down. So categorical cross entropy is what happens when you're choosing from a whole bunch of different sets of classes, right? So suppose instead of just like cats and dogs, I have 100 different animals, right? So in that case, the output is one of a set of many classes, right? Meaning that my true yk might be, just one location in this big vector, right? And this is sometimes called, or not sometimes, this is called, one hot encoding. So it's like saying, OK, this is class number 6. out of my possible set of classes, okay? And then my yk hat is probably going to be, not something that is binary, but after I put it through a softmax, for example, will be a bunch of numbers that all kind of add up to 1. And so this is going to be kind of like whatever inside 0 and 1. And then the loss that I would compute would basically be minus log of, the one hot place. Right? This is like saying, whatever position this was in, I look at the corresponding value here and compute this number, right? And everything else is just getting multiplied by 0. Okay. What else do I want to say? Comments or questions so far? All right, so let me say just a couple more things, right? So the last piece and the critical piece is how do I actually find the theta parameters that minimize whatever loss function I've chosen, right? And of course, that's the hard part. That's what neural network training is, where you kind of press go and this thing cranks away for hours on your big computer, right? So the last piece is basically how do we actually find the optimal parameters? Or near optimal parameters to minimize the loss, right? So in calculus, you know about the gradient, right? So in calculus, we would say, well, the thing I should do is to take the gradient of my loss function, whatever that is, as a function of my parameters, and set it equal to 0, right? Where this is the gradient. Now, that's not usually so easy to do. In practice, what we do is a numerical approximation to this problem called gradient descent, right? And hopefully you've heard of what that is. And if you haven't, we'll talk about it a little bit next time, or maybe I'll try and cram it in just a second. So in practice, we use some form of what's called gradient descent, which is generically what you'd use to optimize any nonlinear cost function, neural network or not. In practice for neural networks, we use an algorithm called backpropagation, which is something specific to how neural networks are set up, which is basically a way of doing this gradient descent process kind of like quickly and easily, okay? All right, so I'm trying to decide whether or not I want to talk about this now, or, well, let me just say one quick word about gradient descent, and then we will talk next time about something that's more specifically about backpropagation, okay? So just like gradient descent preview is, how does that work? So the setup is basically I have, x, which is my input. I have my model. I have my parameters. And then I have my prediction, right? And then I have a loss function between the prediction and the truth. So our goal is to find the parameters theta that minimize this function e, okay? And so to be a little more explicit, gradient descent is basically saying what I would do is I should take the gradient of e with respect to the parameters, which is like saying, well, there are going to be a bunch of parameters, the gradient of e, the derivative of e with respect to theta 1, the derivative of e with respect to theta 2, all the way down to the derivative of e with respect to theta n, or however many parameters there are. Let's call it p, maybe. I know that there is some theta for which I should be able to obtain this number, right? But in practice, this is not very tractable to do, right? it may be very difficult to form the gradient. It may be very difficult to find the theta that sets this equal to 0, right? That's the hard part, right? And so in practice, what we do is to say, I'm going to hopefully have a good estimate of what the answer should be, and then I'm going to take steps in the direction of the gradient, right? So gradient descent is basically saying, if I have theta t, which is our current estimate of the answer. Remember that I'm trying to minimize the cost function. The gradient at a given point is always pointing in the direction of maximal increase. So what I want to do is I want to go in the direction of minimal increase, right? So we want to move a little bit, in the direction of biggest decrease. Right? So my next estimate is basically where I am now minus some step along the gradient of my error function at this point, right? And so this eta, Greek letter, is called the step size, or sometimes called the learning rate. And there are lots of reasons why, this is hard to do. Like, if my step size is too large, then I might overshoot the minimum and have to take a whole bunch of steps to come back to it. If my step size is too small, I'm going to take forever to crawl down the bowl of the minimum, and my training may take forever, right? So kind of, deciding what should the step size be at every given point, how do I tune the schedule of that process, is a whole kind of black art of, again, numerical optimization, right? And so many neural network training algorithms, are based on some form of gradient descent. We'll talk a little about, there are things called stochastic gradient descent and approximate gradient descent. There's all sorts of ways of modifying the fundamental idea. And of course, if you take an optimization class, you've probably heard of Newton's method and stuff like that, where you're using the Jacobian of the cost function. There are lots of ways to do optimization. But what I want to talk about, and I think I'm going to save it till next time, is specifically backpropagation, for one thing, is kind of the underlying guts of how I specifically apply this to a neural network and why it makes sense. And then what I want to talk about next time also is just kind of to my mind, just a deep learning crash course in terms of all of the key words that you're going to see when you read a paper on deep learning that I feel like you need to know, right? So we're going to talk about kind of what are the key deep learning architectures, what are the key words that you're going to come across. Again, this is not a deep learning course. I'm not equipped to teach a deep learning course, right? So I can understand what's going on, and I'm going to tell you just I think what is the most salient, important stuff that you need. And I think that there are probably people in this class who know a lot more than deep learning than I do. So again, I want you to step in and tell me if I'm messing something up as I talk about this stuff. All right, so let me stop here and ask if there are any comments or questions about anything that I've been talking about. Did I make any mistakes? Because don't let me wait till the end of this recording to find out that I made a mistake. Okay. All right. So with that case, I'm going to stop the recording and see you next time.